to Final Mix.
Before there was a North America, before there were the land masses we now call Asia, Africa, Europe, the United States, the Earth was ruled by a great primeval sea. But then the land moved. It rose and fell, heaved and shifted. Volcanoes became islands. Islands became continents. And as they settled, a new Earth was formed. After millions of years of struggle, change, and adaptation, life as we know it evolved against a background of great shaping forces. Some were very present and real, like fire and the sun. Others were less tangible, as was gravity or the great magnetic fields which surround the Earth. Until recently, man could only worship the vast energy of the sun, or the lightning that seared the night sky. He understood very little of the great play of energies over the Earth. Now, suddenly, in but a few centuries, scientific discoveries are helping to explain the world to us. Amazing instruments have extended our senses. Satellites that track storms. Telescopes that search out the secrets of the sun. And we have developed a precise understanding of another remarkable natural force, another kind of energy, a kind that usually can't be seen or felt, but that, like gravity and the weather, has been here since the Earth was formed, a constant background against which all life has evolved, the kind of energy we call radiation.
I'm Goldie Watkins. I'm a health physicist and a member of the Science Advisory Board of the U.S. Environmental Protection Agency. I spend much of my professional life dealing with information about that natural phenomenon called radiation. In fact, I've come 9,000 feet up into the Rockies to take some measurements that'll help me explain to you some rather surprising things about radiation. For although our senses can't detect it, radiation is one of the easiest things in our environment to measure with instruments such as this one. As you can see, I'm getting a reading on the meter. But why is there radiation here? For that matter, what is radiation? And what does it have to do with you and me?
Nothing much, radioactive, that's all.
Radiation.
Just something passing through the atmosphere.
Nuclear power.
I think about poisonous gas, poisonous air.
Atomic bomb, nuclear.
Oh, it's so controversial.
Sometimes dangerous.
Depending on the types of radiation, if it's low-level radiation or ionizing radiation or non-ionizing radiation.
It could also be heat radiating from a radiator.
Well, there's nuclear medicine for one thing.
You can use it to help cure or kill cancer.
X-ray treatments for cancer and also X-rays in teeth and so forth.
Well, I don't care as long as I don't get any.
All right, why is there radiation here? Well, one source is the Earth itself, which contains minerals that are naturally radioactive. The other source is the sky. Naturally occurring cosmic rays are constantly falling on us from out in space. Together, they're what we call background radiation. It's all natural and found everywhere on Earth. But what is this radiation anyway? The word simply means energy that radiates, and there are many different kinds. The light from a campfire is radiation. So is the invisible heat. Radio and television waves are another kind of radiation. as are microwaves for cooking, radar, and satellite communications. All of these different kinds of radiation penetrate matter to some extent. That's why, for example, you can receive a radio program inside your home. But if you ask somebody on the street about radiation, they'll usually think of the kind I've been measuring with my counter, the kind that comes from the inside of atoms, the kind we call ionizing radiation.
Atoms are the building blocks of the universe. Everything on Earth is made of atoms. Tiny bits of matter which are so small that if each of the atoms in a single drop of water were the size of a strawberry, the Earth could be covered with strawberries 20 feet deep. Still, despite their tiny size, we have a pretty good idea of the structure of atoms. They're mainly empty space. They have a central part, the nucleus, with electrons spinning around it. Scientists have identified hundreds of different kinds of atoms, each unique in some way.
Many of these atoms share a fascinating characteristic. Their nuclei, their centers, just naturally give off energy, and sometimes parts of themselves. What they give off is called radiation. This is what we mean when we say a substance is naturally radioactive. Uranium, radium, thorium, some of the names might be familiar. Eventually, because of the fact that they give off this radiation, these substances will attain a totally different and stable form. Certain of them in seconds, others over a much longer period of time. In fact, over billions of years, the uranium in this ore will become lead. During this time, it will emit radiation.
Radiation also comes from cosmic rays. They come to Earth from all over the universe. Rays and particles that radiate out from every galaxy with tremendous speed and power. And this great natural flow of radiation has been going on since the beginning of time. It's particularly intense near a star, such as our sun. During one of the great eruptions, known as solar flares, huge amounts of radiation pour out.
Here on Earth, we're protected from most of this radiation by the Earth's magnetic field and by our atmosphere, which act as shields. But enough gets through to contribute to the background radiation, which has been here since before life began. Let me show it to you this way. The three common types of radiation here on Earth are called alpha, beta, and gamma. And this uranium ore gives off all three. But each of these sources gives off just one of the three types. The first, alpha, can easily be shielded by something as simple as a sheet of paper. Beta radiation passes through the paper, but is stopped by the thickness of this book. The third type, gamma, which is like X-rays, is the most penetrating. It passes through the book, but most of it is stopped by this piece of stainless steel. In each case, what's left is essentially the background radiation. So the thicker and denser the shield, the less radiation gets through. That's why people living at Denver's 5,000-foot altitude get about twice as much cosmic radiation as people living at sea level, in Florida, for example, where they're shielded by a much thicker blanket of the Earth's atmosphere. by the way, another way to decrease the radiation reaching the counter is simply to increase the distance. In measuring radiation, there are several units we could use, but the one for measuring the effect of radiation is the rem. And because we're dealing in such tiny amounts, it's more common to speak of the millirem, which is 1/1000th of a rem. Here at this point, near Canyon City, Colorado, the radiation measurement is equivalent to 480 millirems a year, which is nearly 7 times the average radiation level from the Earth and sky in most parts of the United States. But what is average? If you travel by air from New York to San Francisco, for example, you'll pick up about 2 extra millirem of cosmic radiation during the trip, because of the high altitude, of course. If your travel should take you to Rome, you'll probably visit beautiful St. Peter's Square. Readings taken here show an exceptionally high level of background radiation. It's equivalent to between 400 and 800 millirems per year, or about 5 to 10 times the average background level in the United States from the Earth and sky. This is because the paving stones contain higher than average concentrations of naturally radioactive elements. In fact, building materials the world over contribute to our background radiation level. Grand Central Station in New York City is radioactive. At one entrance, we've measured the equivalent of 525 millirems a year, about 7 times the average background. There's still one other source that contributes to background radiation, the radioactivity in our own bodies. This we get naturally from our air, water, and food. For instance, ounce for ounce, bread is more radioactive than beans, and potatoes more so than fresh fruits. So what does all this add up to? The average yearly exposure in the United States is 31 millirems from cosmic radiation, 40 millirems from rocks and soil, and 28 millirems from inside our own bodies, totaling an average per person of nearly 100 millirems a year. That's average, but it varies with so many factors. Why, if I did something as simple as move from Washington, D.C. to Denver, Colorado, my annual exposure would almost double.
So that's background radiation. It's been here since the Earth was formed. Yet, because we can't sense it directly, we've only known about it for less than 100 years. At Massachusetts General Hospital in Boston, Dr. Edward Webster is a physicist in the Division of Radiation Science. He is also a professor at Harvard Medical School and a member of the National Academy of Sciences Committee, which has for years been studying the biological effects of radiation.
Radiation was first discovered in 1895. Professor Wilhelm Röntgen was working with a cathode ray tube, and he realized that a photographic plate close to the tube, although it was covered with black paper, was being exposed. He then did some experiments which indicated that this mysterious radiation was passing through the human body. And so he decided to take an X-ray of his own wife's hand. And this is the first human X-ray that was taken in the world. You can see the bones, you can see the wedding ring on the hand. This discovery astounded the world. And the next year, 1896, it was found that similar kinds of radiation were being produced by elements such as uranium and thorium.
The idea of an invisible ray that could see through people was irresistible. The popular press had a field day with it. And so did the quacks and charlatans. They had people inhaling thorium gas and swallowing radium salts to treat arthritis and nearsightedness with radiation. And it was believed to be a cure for all human maladies. Scientists were just as excited. Radiation helped many scientists, such as Madame Curie, Thomson, Rutherford, to discover new elements and formulate new theories about the atom. And of course, right away, doctors saw how useful X-rays would be in diagnosis. And within a few years, they were widely used. We know today that very large amounts of radiation can be dangerous. But of course, that wasn't known at first. And a number of these early workers became ill or died from too much exposure. As a result, exposure limits were steadily developed. They were in place in the 1920s and stabilized through the studies of scientists all over the world. Today, there's much discussion about the effects of low-level radiation. Levels we receive from nature, from working with radiation, and from medical diagnostic examinations. We know that very high levels of radiation, levels thousands of times higher than the background radiation we've been discussing, can cause illness or death, and that levels of radiation hundreds of times greater than background may cause cancer in a small percentage of the exposed population. We also know, importantly, that as the radiation level goes down, the risk goes down. The most recent report of the National Academy of Sciences suggests that the risk is even lower than was believed a few years ago. And when you get down to these very low levels of radiation, say a few thousand millirem, there's just no way of telling whether there's any effect of radiation on people at all. Nevertheless, there may be some small effect, and therefore it's prudent for people to keep their radiation exposure as low as they reasonably can. And that's a worldwide policy.
The vast body of knowledge which now exists about radiation permits its useful application to a multitude of human endeavors. Museums use radiation to determine the composition of archaeological artifacts, to detect fake art and discover early paintings beneath later ones. In industry, radiation is used to prospect for oil and to sterilize pre-sealed medical supplies. Critical welds on ships and pipelines are X-rayed to detect flaws or cracks. So are large castings to locate hidden imperfections. And beyond all this, tremendous advances have been made in medical applications and in the knowledge gained through the use of nuclear reactors in industrial and scientific research.
Reg rod at 10 inches, pulling control rod number 1.
Health physicist Jack Luskin of the University of Lowell, Massachusetts.
Nuclear reactors, like this small research reactor, use radioactive materials to operate. They also produce radiation. Uranium, which is one of the many radioactive elements found in nature, is used as the fuel because its nucleus is large and heavy and can be easily split apart. In fact, occasionally this happens all by itself in nature. This is called fission. And when atoms fission, they release fantastic amounts of energy. So the uranium is mined, processed into a solid fuel, and loaded into the reactor. There, uranium atoms are more likely to split apart. In fact, we can make them split each other apart in what is called a nuclear chain reaction. And we can easily control the rate of this reaction. You're watching a working nuclear reactor. Here at the University of Lowell, we use it for research in many sciences, including geology, biology, and chemistry. Even though it's producing large amounts of radiation, alpha, beta, gamma, and neutrons, the shielding provided by 25 feet of water keeps the level so close to natural background that normally we can't even measure the difference.
In a nuclear power plant, a much larger reactor is used to generate electricity. Radiation is a byproduct of this process, the same kinds of radiation that are found occurring naturally all over the universe. In some other kinds of power plants, steam is created by heat from burning a fossil fuel. This steam drives the giant turbines, producing the electricity. In a nuclear plant, the steam is produced by harnessing the heat from the chain reaction. Inside the fuel core of a nuclear reactor, however, the levels of radiation are far higher than those we encounter around us here on Earth. So a modern nuclear power plant is built with a series of barriers to keep the radioactive materials from the environment. First are the fuel pellets themselves and the rods in which they are enclosed. These are surrounded by water and in turn by a steel pressure vessel with walls up to 9 inches thick. Next is a shell of steel plate, and finally the reinforced concrete containment building 3 or more feet thick. Right now, this plant is turning out 1,600 million watts of electricity. All that energy is being released by the atoms of uranium. Standing close to the plant, the reading I'm getting on my counter is essentially the natural background radiation for this location, which averages the equivalent of about 100 millirems a year. And during operation, a plant such as this adds at most 2 or 3 millirems a year to the environment in the immediate vicinity of the plant, or about what we'd get from a cross-country flight, or from standing at the west entrance of Grand Central Station for 36 hours.
Also shows between L3 and L4.
Some of the greatest of all uses for Dr. Röntgen's extraordinary rays are to be found in the field of medicine. Dr. Eric Hall is professor of radiology at the College of Physicians and Surgeons at New York's Columbia University. He is also author of the book, Radiation and Life.
Radiation is one of the most useful tools in medicine to diagnose disease. At the present time, about half the population receives X-rays every year to look for a broken bone or to find a decayed tooth or some abnormality deep within the body that would involve an enormous surgical procedure to find otherwise.
Sort of abnormal.
You think about the gas?
Over the years, there has been a great effort to try to cut down the amount of radiation that is involved in taking X-ray pictures. For example, a chest X-ray involves only about 15 millirem, very small amount of radiation. Other diagnostic procedures can vary up to many hundreds of millirem in some cases.
Take a deep breath and hold your breath. Hold it.
In the case of nuclear medicine, what happens is that a small amount of radioactivity is administered to the patient and concentrates in a particular organ or region of the body. And then, using a special camera, the pattern of the deposited radioisotope can be observed, and much information concerning the patients can be inferred from this deposited radionuclide. The CAT scanner is a major breakthrough and involves essentially a link between a small X-ray source and a computer. And the information obtained produces on a television screen an image that contains far, far more detail than was ever possible with a conventional X-ray setup.
Susan, I'm going to turn the machine around.
In changing the focus to the therapy of cancer by radiation, the first important point to make is that we are escalating from small to large doses of radiation.
While you're having your treatments, you won't feel a thing.
At the present time, about half of all cancer patients receive radiation at some stage in the management of their disease.
Your treatment time will be
in a very substantial group of patients, which amounts to about 80,000 persons per year in the United States, radiation is responsible for a permanent cure.
Don't move.
That is, their life expectancy is not distinguishable from that of their peers that did not have cancer. And this is a very substantial contribution to the practice of medicine. And this results from the use of radiation. In fact, I think it's fair to say that the practice of modern medicine today would be unthinkable, either in the diagnosis of disease in general or the treatment of cancer in particular, without the use of ionizing radiation.
Down through time, from the first primitive stirrings of life on Earth to our own civilization, we've lived in a restless landscape dominated by energy and change.
And as our modern world has evolved, all social and technological progress has come from the development and acceptance of new philosophies, concepts, resources. We've learned first to adapt to our environment and to the great natural forces that surround us, and then to channel them to our use. Radiation is one of these forces, natural and ever-present, all around us and within us, a fundamental force in nature that demands our understanding. As the sculptor and the architect study and come to understand all of the forces and materials available to them, so should you and I, for understanding is the key to the kind of future we choose for ourselves.